Welcome to the second part of the problem-solving section of Chapter 29. Let's begin where we left off with question 5. Here we are given 3 particles that move through a magnetic field which has a constant value and directed along the negative k hat direction. And we see the particle tracks that these 3 particles have left, where particle 1 initially came in to the right. See, that's the first dash, so in the positive I hat direction. Particle 2 came in diagonally with both an I hat and a j hat component. And particle 3 comes in upward, where there is only a positive j hat component, and here this would be both x and y direction. We are asked to determine which of these particles is positive, which is negative, and which might be neutral. And what we need to do is to decide which of these 3 particles experiences a magnetic force, and then what direction is the magnetic force. Well, if you look at particle number 1, it comes into the right, but you see that it bends upward. Well, bends upward means that there must be an FB, which is in the positive j hat direction. Particle 2 comes in diagonally, but notice that there's no bend in the path. That tells us right there that the magnetic force is 0, or in other words, not there. Particle 3 comes in upward, but notice that it bends to the right. Well, there must be a magnetic force to the right, FB, in the positive I hat direction. So let's go ahead and cross each of the velocity components, and we're going to completely omit number 2 because number 2 is the one which is neutral. So the question of which is the neutral one, well, that's particle number 2. So we have to decide whether particle 1 is positive or negative and whether particle number 3 is positive or negative. Well, if you look over here, particle 1 is in the I hat direction. That's number 1. And if we cross that with negative k hat, which is B, we get, negative k hat. Negative k hat direction, which is the direction of B, I hat cross, let's do our little wheel here. I hat cross k hat is minus j hat, but because we have minus k hat, that gives us positive j hat for the direction of FB. Sure enough, FB is in the positive j hat direction, which means that number 1 is positively charged. Well, what about number 3? Number 3, here let's put a number 1, starts off in the positive j hat direction. We cross it with minus k hat. J hat cross k hat. Oops, this arrow's in the opposite. It should point clockwise. J hat cross k hat is I hat, but because we have a negative k hat, this gives us a direction of minus I hat. Now, when we look at FB, the direction is positive I hat. Therefore, it must be that particle 3 is negatively charged because, in fact, it is experiencing a negative magnetic force in the negative I hat direction, as opposed to what the right hand would predict, which is the positive I hat direction. Or rather, excuse me, what the diagram indicates, because the right hand rule indicates that it should be the minus I hat direction, but the actual bending that's occurring is in the positive I hat direction, which means Q must be negative. Now let's come down here and look at this arrangement. We're told that 3 charges, this time you can see they're all charges because they all bend in around the magnetic field, which again, the magnetic field is given to us in the minus k hat direction. Each of these particles comes in with a velocity that's in the positive I hat direction. And notice that the force or the bending is in the negative j hat direction. That's for FB. Well, first, before we even read on what they're asking, let's determine if these, all of these, are positive, negative, and certainly they're not neutral. I hat cross k hat is equal to minus j hat, but because we have a minus k hat, it becomes a positive j hat. Well, you can see that if these were positive particles, they should bend upward in the positive j hat direction instead of downward in the negative. So it must be that all three are negative charges. Now let's read on the question. 3, now we know negative charges, have the identical magnitude of Q and the mass M. They enter the same magnetic field B. Each of them experiences the same magnetic field. It's uniform. And they follow the paths which are shown. Determine which one moves fastest and which one moves slowest. Well, we know that when a charge enters a region where there's a magnetic field, it feels a magnetic force that causes the charge to experience uniform circular motion. The orbital radius of the path is given by the product of mv over qb. Now they tell us that m is the same for all three, Q magnitude's the same for all three, and we know B is the same for all three. Therefore, notice that the only different quantity must be the speed. And if you look over here, the one with the greatest radius is number 1. Therefore, number 1 must be the fastest. Number 1 has the biggest R, and it has the biggest V, since these two are proportional to each other. When we look at number 2, you can see that number 2 has the smallest radius, and therefore it must be the slowest, again, because of that proportionality. What do you think would happen if instead we said that they each had the same mass and the same speed, and of course they are in the same magnetic field? In this case, R would be inversely proportional to the magnitude of Q, and we would have to say the bigger the R, like number 1, the smallest the Q, and the smallest the R would be the largest the Q. So something else to consider, although we weren't asked, how we might look at this a little bit differently. Let's move on to the next question. Here we are told that there's an experiment to determine the value of a magnetic field. First, an electron is released from rest, and of course we know that its initial speed is 0. We know if it's an electron that it has a Q, which is minus 1.6 e to the minus 19 coulomb. So it's released from rest and it accelerates through a potential difference, delta V. Here V is capital V, it's not speed, it's potential, of positive 350 volts. Why? Well, because a negative charge goes from low potential to high potential. So 350 is the high minus 0, the low. It then enters a region where there's a uniform magnetic field that happens to be perpendicular to the velocity. What does that tell us? That the angle between the velocity and the magnetic field is 90 degrees. In this region, the electron undergoes uniform circular motion, obviously because it experiences a magnetic force. And the first thing we're asked, and here you can see a little particle track of this electron, the first thing we're asked to do is, using conservation of energy, determine the velocity of the electron once it is subjected to the value delta V. Well, we know that the change in the kinetic energy of the electron must equal the negative change in its potential energy. That's what conservation of energy tells us. In terms of potential, delta U is defined as Q times delta V. So we can substitute delta U by Q times delta V. And because they tell us that it's initially at rest, well, if V initial is 0, so is K initial, the kinetic energy initially. So it must be there for that delta K is equal to K final, or 1/2 m speed final squared. And that is, of course, equal to minus Q delta V. So to determine the value of V, once it is accelerated through this potential difference, we need to solve for V minus 2Q times delta V divided by the mass of the electron, and we take a square root of both sides. Let's go ahead and substitute our numbers. Minus 2 times minus 1.6 e to the minus 19 coulomb times plus 350 volts divided by the mass of the electron, which, if memory serves me correctly, 9.11 e to the minus 31 kilograms. When we plug in our numbers, unless I've made a calculator error, I get 1.11 e to the 7 meters per second. Now, let's come back over here and read this again. After it is subjected to a delta V of 350 volts and acquires a V final, it enters a region where there is only a magnetic field perpendicular to that V. Well, what happens then is that the V will remain constant and becomes the V for which this electron enters the region where there is only a magnetic field. And they tell us that it undergoes circular motion with a value of R, which is equal to 0.75 meters. Well, we've got that. We've got V. We know the magnitude of Q, 1.6 e to the minus 19. We know M, the mass of the electron, 9.11 e to the minus 31 kilogram, and they asked us to solve for B. So using these quantities right here, how can we determine this unknown magnitude of field? Well, we go back and remind ourselves that the orbital radius of the charge, here the electron, is its mass times its speed divided by the magnitude of its charge times B. So solving for B, we get mv over magnitude Q times R. And this is precisely how we can determine unknown magnetic fields, measuring the radius of curvature, for example, that which could be easily determined from this fluorescing path. And once we get that R, knowing what the charge is and what its mass is and how fast it's moving when it first entered this region, because that would have been our V final, we can then calculate the magnetic field inside the chamber. Well, 9.11 e to the minus 31 kilogram times 1.11 e to the 7 meters per second divided by 1.6, here's the magnitude only, because of course we don't the negative is irrelevant to us here, times 0.75 meters, and we see that B has a value 8.42 e to the minus 5 Tesla. And we could get the direction, if here we've just obtained the magnitude, we could get the direction by looking at the fact that this electron, we know it's a negative charge, is going to curve, and I believe that it is curving in a direction, let's see, downward. It's a little bit difficult, but if we could actually determine where it initially had curved, we could then give immediately the direction of the magnetic field based on knowing the direction of V, which in this case is I hat, and the direction of FB, which again would be minus J hat if it curves downward, or positive J hat if it curves upward. Well, the last thing we're asked to determine is the magnitude of the magnetic force. Well, to get the magnitude of the magnetic force, we take magnitude of Q times V times B times the sine of 90. Remember, we were told V is perpendicular to B. Plug in our numbers, and we get 1.6 e to the minus 19 times 1.11 e to the 7 times 8.42 e to the minus 5 multiplied, and of course times 1, sine of 90, and get a value of 1.49 e to the minus 16 newtons. Next question. Here we are told that a charge passes through a velocity selector. The charge, the single charge, of course there's several, but each individual charge is made up of a gold +2 ion. Well, the +2 tells us that the gold nucleus has, well, actually it's not a nucleus, it's an ion. The ion has an excess of 2 positive charge. In other words, it's obviously lost 2 electrons worth of charge. So that tells us that the Q of this ion is +2 times the E represents 1.6 e to the minus 19 coulomb, giving us a plus 3.2 e to the minus 19 coulomb. The mass of each of these ions is 3.27 e to the minus 25 kilograms. And they tell us that those which make it through the velocity selector that have a velocity of 31,500 meters per second, and remember the velocity selector, you have charges coming in, they pass through an electric and a magnetic field, and those which do not deflect, in other words emerge out, are those for which the magnetic force and the electric force are equal in magnitude. And if these two happen to be these two magnetic field, the magnetic force and the electric force happen to be opposite in direction, it will be true that QVB is equal to QE. Here, we're assuming that the angle between V and B is equal to 90 degrees, so that sine of 90 is 1. Anyway, we're told the value of the magnetic field in the velocity selector is 0.5 Tesla, and they want us to calculate what must be the value of the electric field for these charges to emerge undeflected. Well, from this relationship right here, you can see the undeflected ones will have a QVB equals to QE, which means that E is equal to magnitude VB. Very simple. Well, we know V is 31,500 meters per second. B was given to us as 0.5 Tesla, and therefore E must equal 15,750 which of course we can round to 3 significant digits as 15,800 newtons per coulomb. Last question. Now, our gold ions with a plus 2e, same thing as last problem, and an m of 3.27 e to the minus 25 kilograms, same as the last problem, have passed through the velocity selector, emerging with a speed of 31,500 meters per second. Well, this would have been the velocity selector right here, and the ones that emerge, this is the region where they come into. Now we only have a magnetic field, but this one here has a different value than the one before, 0.1 Tesla. Well, it doesn't matter to us because the B that we used in the last slide was only useful for letting us calculate the electric field because that was the question there. This time the question is, what is the radius? What is this distance right here, or this distance, or that distance? What is the radius of the orbital path? Well, mv equals, R equals mv over qb. And just a quick reminder, where did this expression come from that we keep using? Very simple, folks. If you remember, the only force in this region here is magnetic. So the magnetic force on a charge of mass m produces a centripetal acceleration of that charge, where r is that very radius right there. And if we consider qv perpendicular, the component of qv, which is perpendicular to b, in other words, we're saying we're only going to consider the component that's perpendicular to b, we get mv squared over r. If you look over here, this v is of course the one which is perpendicular because that's the one that experiences the centripetal acceleration. This v cancels one of those, and so solving for r, we get m, one of those v's, the perpendicular one, over, and I'm going to write this as magnitude q times b. And guess what? That's where this came from. So if you need a little reminder as to where that came from, that's where it came from. Anyhow, let's go ahead and just plug in all of our numbers. 3.27 e to the minus 25 kilograms times 31,500 meters per second divided by 3.2 e to the minus 19 coulombs times B, 0.1 Tesla. And I get a value of 0.322 meters. Well, that concludes the second part of the problem solving session for chapter 29. Until next time.